Hello, I'm Tom Benton. I'm a researcher at Cambridge Assessment, and I want to describe to you some work we've done over the past year to explore whether some A-level subjects are harder than others. This work was prompted by research by the exams regulator Ofqual, and it concerns a method called Comparative Progression Analysis. So what is Comparative Progression Analysis? Well, it's based on looking at how grades in any A-level subject relate to grades achieved in the same subject at GCSE. In other words, how much progress do pupils make between GCSE and A-level in different subjects? And then if we see some subjects where it looks like students are making a lot more progress, we might worry that the A-level is easier than others. Here's an illustration. This chart shows the grade distribution at A-level of candidates who achieved a grade B in the same subject at GCSE. The red lines relate to the distributions for maths and science. In these subjects, candidates with a B at GCSE are most likely to get a D. There's even a reasonable chance they'll end up with an E. The blue lines relate to subjects like history and English literature and arts. In these subjects, students with a B at GCSE are most likely to get a C. Getting an E is quite unlikely. At face value, this chart suggests that maybe some subjects, English literature, history, are easier than the sciences, perhaps with modern languages in between. And it's this chart that led us to want to explore whether there might be a problem that needs addressing. And that's what led to this research. The first thing we learn when we do this work is that the pattern we see in the previous graph isn't repeated if we start with students who achieved an A star at GCSE, which is much more common amongst people who go on to do A-level. In fact, if we look at these students, it's possible even that the sciences are easier. The red lines relating to the sciences are associated with the highest chances of getting an A star at A-level, just marginally. So, we know we can't do this analysis for GCSE grades individually because we get a different result if we use GCSE grade B from if we use GCSE grade A star. We need to analyse across all grades at once, and to do that we need a table like this one here. It shows across all subjects the proportion of students getting each grade or above based on their achievement in the same subject at GCSE. For example, right in the middle of the table, across all subjects, a B at GCSE means a 2/3 chance of a C or above at A-level. Next, using the information I've just shown for a range of A-level subjects, I looked at the distribution of GCSE grades students had achieved in the same subject. And you can use that table, and thus you can work out what proportion I'd expect to achieve each grade at A-level if the pattern of progress was the same for all subjects. This gives me the column labelled expected. We then compare the expected percentage, getting each grade or above, to the percentage of candidates who actually achieved each grade or above. There's a few things we can learn from this table. At grades A and A star, we can see it's not the case that sciences always show achievement below the expected rates, while humanities, like history, are always above. In fact, maths and biology are both show above expected numbers of A star. In fact, it's French that is below the expected value. Similarly, if we look at grade A, then expected and actual figures are actually very close together for both maths and history. It's at the lower grades that we see the bigger differences. For example, at grade C. So, for physics, the actual percentage of students getting C or above is noticeably below what we'd expect if all subjects were making the same progress. Whereas for history, it's noticeably above the expected value. To think about why this might be the case, we need to move beyond just looking at grade distributions and take a closer look at student performance in terms of marks. This chart compares the mark distributions of physics and history at A-level based on final year examinations. We can immediately see the difference between these subjects and why it is that we see a difference in grade distributions. In physics, we have a noticeable number of candidates getting very low numbers of marks, so less than 50 out of 200, only 25%. In other words, getting the majority of questions wrong. And we can understand why an awarding committee might not want to give passing grades to scores this low. In contrast, scores that are very low are very rare in history. Almost nobody scores below 50 out of 200, and 95% of candidates will get at least 100 marks out of 200. In other words, when students write essays in the history exam, the vast majority of candidates are producing work that has at least some intrinsic merit. It's understandable why awarding committees don't want to fail candidates who have produced reasonably good work. As an aside, some might complain about this analysis that we could simply change the mark scheme and get these marks spread out. However, other research has shown that if we set aside the mark scheme and simply ask experts in the subject, history experts for example, to judge which of two essays is holistically superior, who's the better historian, then if marks are close-ish together, then it's difficult to make that judgment. In other words, the spread of marks isn't just because of the mark scheme or because of the assessment, it's because a lot of the work that is produced is of fairly similar quality. In particular, there really aren't lots of essays that are obviously bad. Now, with these different distributions in mind, let's look at what would happen to grade boundaries if we statistically lined up the grade distributions to the expected values that I showed earlier. In this chart, the red lines are essentially the current boundaries, and you can see they're similar across subjects. The only change I've made is this was before AS levels were removed from A levels, so there's been a slight adjustment there, but they're essentially the real boundaries. And you can see they line up, and that's probably not an accident. The blue dotted lines are where the grade boundaries would move to if we made everything fit statistically with expectations, assuming the same progress in every subject between GCSE and A level. As you can see, the top boundaries, A and A star, they wouldn't move very much. However, the bottom end is where you see dramatic changes. For physics, the lowest grade boundary, the E grade boundary, would be down to nearly 50 marks. For history, over 100 marks would be needed even to get a D, and candidates getting more than 80 marks would be failed outright. Finally, we see the narrowing of the gaps between grades in history. So, for example, there would be only 21 marks between failing your A-level history outright and being awarded a D. In other words, we'd end up with very different grades for pieces of work that, when viewed holistically, outside of the narrow remit of the mark scheme, aren't that different in quality. This probably isn't something that's desirable. Aside from these concerns, we've also done other research looking at whether we can use comparative progression analysis to definitely conclude that one subject is harder than another. And we're going to be able to show that that's not the only way to interpret these statistics. So for this experiment, we simulate GCSE and A-level results in science and humanities for 500,000 imaginary pupils. More details about how this is set up are in the full report on our website. We're going to set the simulation up so that both A-levels are equally difficult. So note that the grade distribution for A-level along the bottom is the same. For example, in both subjects, 20% of students get an A or above. However, we're also going to set the simulation up so that there is a lower correlation between GCSE and A-level in humanities than there is in science. So, for example, we see several hundred of those simulated to get a B in GCSE humanities are simulated to get an A star in the same subject at A level. In contrast, we have a high correlation between GCSE and A level in science. So, of those who are getting a B in GCSE, very few will go on to get an A star at A level. The low correlation that we see here reflects what we saw right at the start in those charts, that big movement in the A-level grade distribution for sciences between those getting a B and those getting an A star, but less movement for humanities. this low correlation is going to be really important for the results we get next. Now, we imagine that students can choose which A-level they do. It's a simplified situation, choosing one A-level out of 2 options rather than 3 A-level options out of loads. For this simulation, we imagine that students always make wise choices. In other words, they pick to enter the subject that they're going to do best in. Now, we look at the relationship between GCSE and A-level when restricted to people who choose that A-level subject. So not for everyone anymore, just for those who are making the wise choice. When we do this, we see very similar patterns to the ones we saw in practice. There's a big difference in grade distributions for people with a B at GCSE in terms of what they'll get in A-level. If we look at those who got A star in their GCSE within this simulation, then we see very similar distributions of grades. Again, that reflects the actual results we saw in practice. So we end up with these charts again that look like humanities are easier. Got this advantage for the grade B students, nearly the same for the A star students. It looks like that, even though we know from the start we've specifically set up this study so that the 2 subjects are equally difficult. So, what's going on? It's all about the low correlation between GCSE and A-level in humanities. In humanities, we've seen there are some students capable of making big progress between GCSE and A-level. All these students are going to make that subject choice. They're going to study humanities. There are also students who, because of the low correlation, high grades at GCSE don't guarantee a high grade at A-level. They might not make so much progress. If we assume students are making wise choices, these students are not going to choose to study humanities. When you put these 2 things together, it makes it look like you get a lot of progress in humanities. In contrast, for science, because GCSE and A-level achievement are closely tied together, there isn't the room for the subject choice to make so much difference to the progress. So we don't see the same effect. So to conclude, different statistical progress may not mean subjects are of different difficulty. In fact, we could get the same patterns from different correlations between GCSE and A-level for different subjects, and from the fact that students might make good choices about which subjects to study at A-level. We should caveat this by saying we don't know if this is the cause for the patterns that we see, but it is a possible explanation for some of the differences between subjects. So to summarise, we've seen from mark distributions that very poor performance is rare in history. There's a question about whether this is something we should adjust for statistically. More importantly, we need to think about whether it's educationally beneficial to tell those whose performance is reasonable that they've completely failed their A-level. We've also seen that statistical results can have more than one explanation. This means deciding on how to respond can be tricky. Now, I've only shown one way of looking at inter-subject comparability here. There are other ways, other statistical ways of doing the same thing. For example, using all the GCSE subjects to make predictions, or using all A-levels to predict another A-level. For more details of these methods, look at issue 22 of our Research Matters publication. We should note that all these methods run into the same troubles. A longer report describing this research is available on our website. To see that or look at any of our other research, go to cambridgeassessment.org.uk/our research.